Hello everyone. So this is the next video on uniform continuity. In the last class we discussed a few properties on uniform continuity. Today we will discuss few more properties and we will try to solve a few problems on this uniform continuity. The first remark is, it reads as this: if a function is continuous on an interval, so consider a continuous function in an interval I, and you find the derivative in the interval I naught. What is this I naught? I naught is the interval obtained by deleting the endpoints of I. If you find the derivative in I naught, if the derivative is bounded in I naught, then f is said to be uniformly continuous. Idea is clear? Consider a continuous function on the interval I and check the derivative in I naught. If the derivative is bounded in I naught, then you can conclude that the function is uniformly continuous on the interval I. However, the converse is not true. What is the converse? If the derivative is unbounded in that I naught, can we conclude f is not uniformly continuous? No, we cannot conclude f is not uniformly continuous. That is, converse need not be true. That is, I consider an example here. F of x is equals to root x on the interval 0 to 1. This function is likewise on the interval 0 to 1. This function is continuous and it is, in fact, it's an uniformly continuous function. But if I think about its derivative, f dash of x, it is 1 by 2 root of x, which is unbounded. However, the function is uniformly continuous. So converse of 1 is not true. Second remark is, I just want you to remember in this way, to consider a periodic and continuous function that is always bounded. A periodic and continuous function is always bounded. For that you can think about sin x, cos x. It is periodic and it is continuous function overall in your R, and it is bounded. However, a periodic and continuous function is uniformly continuous on R. Next criteria is sequential criteria, which says this: if f from A to R is a function, then f is said to be uniformly continuous. F is said to be uniformly continuous, and it's an if and only if statement. F is a function from A to R, where A is some subset of R. Then f is uniformly continuous on A if and only if you have two sequences xn and yn such that xn minus yn converges to 0, then f of xn minus f of yn must converge to 0. That is sequential criteria. We'll use this to solve a few problems later on. The fourth remark is, if f is an uniformly continuous function and it is defined on a bounded set, it's an uniformly continuous function defined on a bounded set, then f is bounded. That is, you consider the image of uniform continuous function on a bounded set, that is bounded. If f is uniformly continuous, then f of s, where s is a bounded set, then f of s is also bounded. Idea is clear? Sometimes question may arise in this way, so I added this remark. If you have a uniformly continuous map, It maps a bounded sequence to a bounded sequence, a convergent sequence to a convergent sequence, and a Cauchy sequence to the Cauchy sequence. Then we have some problems. We will try to solve them one by one. The first problem already we discussed. F of x is equals to x, whether it is uniformly continuous on every subset of R. This we solved. If you just look to previous video, you will get to know how f of x is equals to x is uniformly continuous. And the second you try to solve this. See, f of x is equals to x square, x cube, x to the power 4. These are uniformly continuous on any bounded interval. On any bounded interval a to b, but this is not uniformly continuous on any unbounded interval like a to infinity or else minus infinity to a, right? Something like this. So the function is not uniformly continuous. These kind of functions on unbounded intervals. Next we have in the third we have 10 to 12 problems. We will try to solve this. Examine the uniform continuity of the following. So we have f of x is equals to 8 power x on the open interval 0, 1. See, if you just look into all these things, I just took the problems which is behaving in the bounded interval. The intention is to just to make sure that whether to use this result and to solve that problem using only by that result, so that it will make us to just to think about that results in a comfortable way, and once we are solving some problems we can use that result. The result is, we already discussed this, uniform continuity on bounded intervals. What else it says? F is a function defined from f is a function defined on finite interval. Let us assume that interval is a, b, where a and b are finite. Then f is uniformly continuous if and only if the first thing is f is continuous first of all it must be continuous. Second point is limit of f of x extending to a plus must exist. Limit of extending to f of x extends to b minus, the left hand limit must exist. So the limit points at the end, limit at the end points must exist. And this is an if and only if. If f is uniformly continuous, then these three things will be satisfied. If these three things are satisfied, then f is uniformly continuous. ಈ ಮೂರು ಕಂಡೀಷನ್ ಸ್ಯಾಟಿಸ್ಫೈ ಆದರೆ ಬೌಂಡೆಡ್ ಇಂಟರ್ವಲ್ ಅಲ್ಲಿ f is uniformly continuous. f ಯೂನಿಫಾರ್ಮ್ಲಿ ಕಂಟಿನ್ಯೂಸ್ ಆದರೆ ಈ ಮೂರು ಕಂಡೀಷನ್ ಸ್ಯಾಟಿಸ್ಫೈ ಆಗುತ್ತೆ. ಅರ್ಥ ಆಗುತ್ತಾ? ಸೊ ವಿ ವಿಲ್ ಜಸ್ಟ್ ಯೂಸ್ ದಿಸ್ ರಿಸಲ್ಟ್. ನೋಡಿ, f of x is equals to e power x on 0 to 1. This function is continuous. Approach from left, e power 0 is 1. Approach from right, e power 1 is e. So all these three conditions are satisfied. So it's an uniformly continuous function. Come to the second one, sin 1 by x. As you approach x from x, sin 1 by x from 0. Sin 1 by 0 is sin infinity. So that does not exist. So this is not uniformly continuous. This one, f of x is equals to x into sin 1 by x. See, this is not defined, but x into sin 1 by x, as x tends to 0, 0 into some quantity, bounded quantity, that will be 0. So this is continuous, and as x approaches 0, this is 0. As x approaches 1, it is 1 into sin 1. The function is uniformly continuous. Coming to that, f of x is equals to e to the power 1 by x. This function is continuous on the interval 0 to 1. As x approaches 0, what will happen to this? E to the power 1 by 0, it is e to the power infinity. This is not, that does not exist. Second condition will fail for this. So this function is not uniformly continuous. This one f of x is equals to 1 by e to the power x on 0 to 1. This function will be uniformly continuous. Check with that. This one f of x is equals to e power x into cos 1 by s. As x approaches 0, cos infinity, e power 0 into cos infinity, that is 1 into cos infinity, which is 1 into some undefined quantity, which is not defined. So this function is not uniformly continuous on the finite interval 0 to 1. How about the case for f of x is equals to cos x into cos pi by x? As x approaches to 0, this is cos 0, it is 1. But cos infinity, this function is not defined. Cos of infinity, 1 into cos infinity you will get. So that function limit is not defined. The second condition will fail for this. Similarly, second condition will fail for the 8th problem. This function is not uniformly continuous. If you consider f of x is equals to sin x into cos pi by x. See, as x approaches to 0, this is 0 into some quantity cos infinity. So this is 0 into some quantity. So that is 0. As x approaches 1, this is sin 1 into cos pi. Cos pi is minus 1, so you will get minus sin 1. So this function is continuous in the interval 0 to 1. So all these three conditions are satisfied. So this function is uniformly continuous. F of x is equals to cot x. See, if I plot the graph of f of x is equals to cot x, this is pi by 2, and it looks like some chair function. Chair. Okay. So this becomes parallel to y-axis in the interval 0 to pi by 2. It is asking from 0 to 1. However, at 0, the curve becomes parallel to y-axis, so which says if the graph becomes vertical, then it fails to be uniformly continuous. So this function is not uniformly continuous. E to the power minus x, as x approaches 0, it is 1. As x approaches 1, it is 1 by e, and the function e to the power minus x is continuous. So this function will be uniformly continuous. 12th one, f of x is equals to tan x, which similarly looks like the you can analyze using the cot x way. Tan x is, it looks like this, right? So at pi by 2, that will looks like an asymptote, means the graph becomes parallel to y-axis, so the function is not uniformly continuous. Yes, we will discuss few more results on uniform continuity, and we will solve a few more problems on uniform continuity. So this is some problems using that one result to make sure that can we solve this kind of, does it will give the enough confidence to solve this kind of problems. We'll try to solve few more problems in the next class. Thank you.